afternoon.
Good afternoon.
So we were continuing on chapter 3. We were on this example, which was a composite cylindrical wall composed of two materials. You have this thermal conductivity A and B. There's a very thin electrical heater in between, and they give us the schematic you see on the screen that I ended up drawing. They have liquid pumped through the inner tube, and then we have some convection on the outer surface of all those tubes, so on the outside surface. And they wanted us first to do under steady state. We have the thermal circuit, which we did, okay, for part A. And then part B is to solve for an expression to solve basically for TH, for the temperature of the heater. Okay, and then C is that ratio of heat outer over heat inner. All right, so we set up our thermal circuit, and we have the heat coming in on our very thin heater at a single point because of that, and it goes either to the outer surface or to that inner surface. We have heat transfer, so inner and outer, okay, and it's all per unit length that we've set up. Okay, so then part B is to solve for that expression to basically get us a way to solve for TH, the temperature of that heater, in our thermal circuit. So where do we begin to solve this?
Does it really matter which side we choose?
Well, maybe. We weren't given Q outer or Q inner, right?
Okay.
So, but where do we begin? Like, you said doesn't decide which to choose, but if we started with the heat, right? Well, heat is delta T over R, right? All right, so what heat and how do we want to arrange, where do we want to start on this with what delta T over R?
We can find Q out, right? Using in minus out as our change in temperature.
In minus out. So which delta T are we using? The inner T infinity over outer or minus outer?
Yeah.
So we got to follow the heat is the other thing, right? So we have this QH coming in, and it's going this way, and it's going this way. Okay, so if we did delta T across inner to outer, it doesn't flow with the heat that we have going on. And
would it be inner minus TH or outer minus TH?
Yes. Okay. So if we set this up, let's first just start with Q's. We say the QH of the heater is the Q inner prime plus the Q outer, right? Because we have the heat going in from the heater, and that's going dissipated out to the outer or the inner. Okay, and then if we, as mentioned, do the inner side, now we have TH minus T infinity inner over our I inner plus R B inner, okay? And we do it again for the outer side. Okay. Makes sense? Okay. All right. So next thing we need to kind of describe, so I should also say, and that's what makes this problem a little trickier, is because we have this heat coming in the middle contact point, where other ones we might have just had a plain wall or something where you just have heat kind of going in one direction on your your circuit, so you don't have to worry about the point, but it's still high. The heat is going from high to low, and TH is our highest temperature, right? All right. Okay. So one other thing we need to kind of look at is we have this heater QH prime, right? In the problem, we were given QH double prime. So how do we go from one to the other? Because we're not given, we're given, as you see right here, QH double prime, right? Which is heat flux, okay? And we need heat per unit length.
So do we just multiply that by the circumference?
Yes. Okay. So normally, yeah. So if you're thinking about, heat is heat flux times your surface area, right? And we were given heat flux, surface area would be 2 pi r, I guess, outer over your length, right? But if you want Q over L, which is Q single prime, that's just your heat flux times 2 pi r outer. Okay. So let's write that. Okay. All right. So what's next for this expression? So on our schematic, we were given, it labeled T infinity, inner, outer, convection coefficients. We have the heat flux. So we have those, right? So it labeled this. We're basically an expression to solve for this. It labeled this. So that's shown as a given. It labeled our outer, shown as a given, but we don't have these labeled on our schematic, right? So we have to come up with something for that. Okay. All right. So our inner resistance is from that flowing fluid. Well, so what's that general equation look like?
Length over H.
Yeah.
H of I. So in this case, would it again just be the circumference divided by HI?
Yep.
H inner? Okay.
Yeah, so we'll show it again over here. So convection, without the prime, it's always just 1 over H A, that being your surface area that the convection is going on, which is that outside, or this is the inside. So that's that inside surface area. And so if we did this, this will look like 1 over, so again, this is, so in general, in this surface area, because it's a cylinder surface, 2 pi r inner, and then length, right? But we're pulling the length out, okay, because it's r prime. Okay, so we do this. Okay, so that's our resistance equation, okay, for per unit length of our, or for the length, per unit length heat for the inner, okay. Now we have B, let's do, what's that gonna look like?
Area divided by K.
No, so you're thinking of a plane wall with conduction. Let's see. Looks like L over KA, right? That's for plane wall, okay? So we have a cylindrical in the R direction. So we got to go to table 3.3, okay? And
ln R2 over R1.
yep, so we have the natural log, because as we saw from the lecture notes, the heat equation, you know, when you integrate twice, it comes up with a different solution to the temperature distribution. So it comes up with a different dT over dr. Okay, so we have a natural log ends up being what we have. So this is natural log R2 over R1. And then it's 2 pi kb. And then it, if it wasn't per unit length, we would have a L there also. Okay. All right, so then we can do similar to the other, to the A material, so that's conduction, and then to the outer convection. That was conduction, this is convection. All right. Okay. So now, if we look at these equations, we had convection coefficient label on our schematic, all our radiuses, so that should have been R1, right? Yeah. All our radiuses given, thermal conductivity, and that should be R3, this problem. Same with over here. All right. Okay, so that's given. So now we basically have an equation where our only, if we put all these, you know, this equation and our resistance together, so all those equations together, the only unknown then is the temperature of the heater. Any questions? Okay, so then we have the part C, okay? So part C is this ratio, right? Outer over inner, okay? And it's just a rearranging, okay? So we have, this is inner, this is outer, right? So we just put those together. So outer So just taking this equation and dividing it by this one. Okay, so taking this one and dividing it by this one, we get a setup that we see here. Okay, so the last part of this question is how might we minimize this ratio? If we wanted to minimize this ratio, Q outer over Q inner, what would we try to increase or decrease? Assuming we're stuck with the temperatures.
Can we decrease T infinity outer and yeah.
Yeah, that would be a way, not decrease. You would want to increase temperature outer. Or you say R outer?
Yeah, I said a T infinity outer, but
okay. Yeah, you'd want to increase that, but let's assume we can't mess with the temperatures at all. So the only things we can kind of mess with, let's say, because our system only really the design, like the heater and the T infinity is more like a fluid or the outside air. So let's just assume those things are kind of set with our application, right? And now we're just, go ahead.
So either we can increase the R outer plus RA, or drastically decrease R inner plus RB.
Yep, or any kind of combination of those kind of things. So if we look at decreasing, say we decrease Ri, it will also be decrease RB, right? And then it would be increase RO, increase RA. Right, so that's kind of an overall, right? I want to get it to the parameters. So we want to decrease Ri. So let's look at Ri. That's this one right here, right? So if we're looking at Ri and we want to decrease it, what would we change? What can we change in it to try to help us?
Increase the inner radius.
Yeah, so we can increase the inner radius, or let's say HI. Okay.
So that would be to like change the fluid going through the inner radius, right?
Velocity you can do
Okay.
it with. Yeah, not it could be changing the fluid, but most likely it's changing the velocity. So increasing those two parameters, right? All right, so we want to decrease RB. So if we're looking at RB here, what do we want to do to decrease this?
You could increase K.
Yeah, so increase K, right? And there's also looking at the natural log, you want to do R2 over R1, you want to decrease that, okay? That ratio. Okay, so that's KB is, higher thermal conductivity materials. So aluminum, copper, something higher in thermal conductivity would help us. All right, so then increasing RO, all right, it's convection again. So now it's decreasing HO or R3, right? So we want to decrease that, or we said decrease R3. Then there's RA, which is the same. So now we were increasing this resistance, right? So we do the opposite of what we were doing with RB, right? Okay, so that kind of tells us now the parameters we want to mess with. So this would be, higher insulation. That's that KA, making its thermal conductivity go down. That's kind of like an insulation, right? And, having higher thickness insulation, right? This is showing us having thinner, high conducting material would be beneficial. High thermal conducting, okay? Or on the outside, having stagnant air, like not as much of a higher velocity, so not high convection, right? So keeping that velocity down, having more stagnant air. Okay. Any questions on that?
So would this be like a requirement or a constraint that we might have on a heat exchanger?
Yeah, or I mean, this is potentially, there's different things you have constraints on and different problems. So this one is a constraint of, let's say you had a heated line. So in my field, it might, heated line is pretty common. Maybe you want to raise the temperature of a flowing fluid. Maybe you need to keep it at a set temperature. Okay, so this would be a heater on a line with insulation around it, like as the fluid's flowing through it. So this is a common thing for something like that. And what are the parameters now that influence your design? What can you now change in your parameters to help your design? So that's where it's kind of like a parametric study with just kind of looking at the parameters in general from the equation that governs it, right? As opposed to because you could just put these values in and just vary them and see how this ratio changes. Or we're kind of looking at the equation itself and just looking at, by changing these parameters, what in general would happen with the equation, right?
Got it, thanks.
Any other questions? All right, let's do .60. A spherical tank of 4-meter diameter contains a liquefied petroleum gas at -60 degrees Celsius. Insulation with a thermal conductivity of 0.06 watts per meters Kelvin and thickness of 250 millimeters is applied to the tank to reduce the heat gain. Part A is determine the radial position in the insulation layer at which the temperature is 0 degrees Celsius when the ambient air temperature is when the ambient air temperature is 20 degrees Celsius, and the convection coefficient on the outer surface is 6 watts per meter squared Kelvin. Part B is if the insulation is pervious to moisture from the atmospheric air, what conclusions can you reach about the formation of ice in the insulation? What effect will ice formation have on heat gain to the liquefied petroleum gas? How could this situation be avoided? All right, so we have a spherical tank. So we have a spherical tank. We have a diameter of 4 meters. Tank temperature -60. The insulation is 0.06 watts per meters Kelvin. The thickness ends up being 0.25 meters. T infinity is 20 degrees Celsius. The convection coefficient is 6. They want us to find the radius, and I'm going to call that RZ, where the temperature, which I'm going to call TZ, is equal to 0 degrees Celsius. And then part B is the effects of ice. All right, so our schematic. With our nice sweet circle here. We have our perfectly drawn circles. Let's see if I can. Yeah, I'm not going to mess with it. All right. All right, so if we now label it, so we have Ri, so that's the inner radius, the outer radius, over here is our T infinity and H. So this is our insulation. The temperature of the tank, oh, and then the thickness, right? Okay, in this system we see the insulation, spherical tank inside is our liquefied petroleum gas that is at our negative 60. Then we have our outside at 20 degrees Celsius. Okay, and we have a thermal conductivity, convection coefficient on the outside, and a thickness. Okay, so we can, put our assumptions that we have for this section, right, in the chapter, which is our 1D steady state constant properties, right? And no thermal energy generation, right? So that's what we applied to the heat equation to get us the solutions we can do here, right? All right, so where would you start to solve this? we have, oh, go ahead.
Thermal circuit.
Right? We have these four assumptions, right? That tells us let's draw a thermal circuit. It says that's the easier way to solve this. We have these four things that can be applied. Let's go to our thermal circuit, and that might help us to, solve the problem from there. All right, so thermal circuit, right? How many resistors in this thermal circuit?
Three.
2.
So they basically didn't tell us anything about what's going on inside the tank, right? So we're going to have to assume that the inner surface is at the temperature of the tank. Okay, so that removes one of the resistors. Okay, we don't have any convection basically going on the inner surface of the wall. Looks like a mountain range. All right, so we have our tank over here, T infinity over there, our insulation, and our convection. All right, what else do we got to draw on this thermal circuit?
The heat transfer.
Yeah, and where is that heat transfer going?
From T infinity to T tank.
Yeah, so we have heat going into the tank, right? Okay. And it's staying at -60 because we're basically assuming it's it's changing phase, so it's still staying at the same temperature with any heat gain, but it's just vaporizing some from liquid to vapor. All right, so we have our thermal circuit generalized here. Now what?
Write out an equation for Q.
For Q, okay. So Q, you said left to right, so that's T infinity minus T tank, and then the resistance is across it, which is our insulation plus our convection, right? So in this case, we have T infinity, we have T tank, we don't have Q, we don't have our resistance equations yet. So let's write down the resistance. So the resistance for the insulation, what do we got to look for to get this equation? What's this one going to look like, or where do we go get this?
For spherical, it's going to be 1 minus R, 1 over R1 minus 1 over R2, whole thing divided by 4 pi K.
Yeah. So we have.
So my question for that would be, is R1 supposed to be the smaller radius, or is R2 supposed to be the smaller radius?
It's still like the higher minus bigger minus smaller.
Okay, so in this case, our R1 will be our outer.
So sorry, wait, let me.
The notes looks like it shows R1 is the smaller of the two.
Yeah, so it's going to be R1 minus R outer. So it'll all be to keep the R a positive, okay? So R outer is a larger number, so that makes that end up being this a smaller number, right? If R outer is larger, that makes that a smaller. So you want the R of the insulation to be a positive value if you're going by just arrows and directions that way, right?
Got it. Thanks.
And then we have 4 pi K insulation. And then, well, we can solve this. We have our inner, right? It's just our diameter divided by 2, which ends up being 2 meters, right? And our outer is our inner plus our thickness, right? Which is 2.25 meters. Check. Yeah. Okay. So then we can solve this and we get 0.0737. Okay. All right, convection. You know, what's this one look like? Right, our convection always is the convection coefficient, 1 over the convection coefficient surface area. It's then what's that surface area, right? Equation.
4/3 pi R.
Yeah, so that's 4/3 is it 4/3? Is that for volume?
Plus 4 pi r cubed for surface area of a sphere.
Yeah, yeah. So we have then 4 pi r outer squared. Yeah. So that's our surface area. So that's one couple of those kind of geometry equations you kind of want somewhere close, maybe on that same table of, you know, I should write down the table 3.3 again. You know, it's just so you're not trying to find that surface area of a cylinder, surface area of a sphere, volume of a cylinder, volume of the sphere. So those, you know, just to have them quickly for you would be a good thing to have nearby, either marked in your book, like as a note, or on a equation sheet you make. All right, so if we look at this, we also have all these values. Okay, so we end up getting .00262 Kelvins per watt. Right, you see, you know, it's an order of magnitude lower, or and versus the insulation's resistance, right? So now we know those resistances, we can solve for Q. Right? So we get 1048 watts, right? Which is great. We have Q, but part A is asking us for the radius, RZ, in the insulation where the temperature is 0 degrees Celsius.
So now we essentially just redo everything but we have to sub in T infinity with TZ and solve for R.
Yeah, so yes. So we basically, look at it. You basically have right in here some location where to the temperature, this TZ is equal to 0 degrees Celsius, right? So if you want to even visually see it better, you could look at it as another thermal circuit where you basically have two insulation thermal resistors. And then this is T infinity, so you have, an insulation to Z, some other insulation thickness, so I'll call that 2, and then convection, and we're basically looking for this point where TZ is. Okay. Q. All right. So then, as you said, we can. Oh, was there a question?
Yeah, I have a question. So from the right side, we know what T infinity is, but that point between R insulation and convection, is that temperature also going to be TZ, or is it going to be something else?
It'll be something else. Okay, so if we go, back up here, right, the temperature is dropping as we go from here to here, right? So there's a delta T always for that heat to move from right to left. So at this point, it's going to be a higher temperature than this point, right? Which is a higher temperature than this. You can work your way through. Okay.
Yep, thanks.
Yep. Okay. So then if we set up our thermal circuit, we could do it from, here I have it from TZ to T tank, as was mentioned. So from here to here, you could do it from, from here to here also. It just adds in another resistance of R convection to utilize, but we can just do it from either way and set up the equation to solve. Okay, so if we do it from this side, then we just have this R insulation Z, right, that we have to have an equation for. Okay, and that's our setup here. Okay, so we have, if we put these two equations together, right, we, these up here green, okay. We know TZ because it's 0, temperature of the tank. We solve for Q already, right? And then the resistance is down here. We have Ri, don't have this. We have our thermal conductivity. So putting those two equations together, the only unknown is Rz, right? So even if we started here, right, we would have saw, oh, we need to get Q. So let's do it over a temperature range that we do know. And that was the part we did above, right here. Right.
Professor?
Yes.
For between TZ and T infinity, that temperature, that is something else. How come that's not included in our heat equation?
Like this point right here?
Yes.
Because we didn't need it. I mean, we can solve it, but like if we did it, we did this, this one right here, because we did it across this point.
Okay, gotcha.
Right. So across that point, all we need is that resistance. But if we did it across here to here, we would need this. This is 2, and then we need this one. Okay, so we'd have to have those two resistors on the denominator. So we could do it. It just makes the equation a little more complex to solve, because that R is kind of buried in there even more. All right, so we now have just one unknown between those two equations. So if we solve for it, we get 2.189 meters. And then the last, any questions? All right, so then the last thing it asks is, what, if the insulation is pervious to moisture, that means, moisture can make its way through from the atmospheric air. So moisture, because there's moisture in the air, what conclusions can you reach about the formation of ice in the insulation? What effect will ice formation have on heat gain to the liquefied petroleum gas, and how could this situation be avoided? So we'll start with the first part. Is like, if it's water vapor is able to make its way through the insulation because there's air can make its way through. What does this? Where is there ice being formed, and where is that ice being formed?
The water freezing in the inside the insulation if water particles are getting into it, and then
Yeah.
makes it. Yeah.
Yeah, where is it freezing? So what location? Go ahead. Sorry.
Oh, it wouldn't be freezing like just in the insulation in between the wall and inside of the tank.
Yeah. Yes. So it would be freezing between TZ and T tank. So it would be, right here would be our ice. Okay, because they strategically picked temperature of 0, right? That's when ice, water freezes. So 0 degrees Celsius. So then we have from 0, which is right here, and then over here it's our negative 60. So in that location, we would have ice, right?
Why wouldn't there be ice between TZ over the second resistance between TZ and T infinity?
Well, it's because it'd be above freezing. Because the temperatures, from here over is above 0 degrees Celsius. So, okay, so if we say that's, ice is just in any of the voids within the insulation, which insulation usually is a lot of just air voids. What will this ice formation have on the heat gain to this liquefied petroleum gas? Will it change it? And how would we go about seeing how this would change it?
If ice forms, then that would reduce the heat gained on the inside of the tank, right?
It would reduce it? Maybe. So the way to check would be now this R insulation is really R of ice, which means that's going to be 1 over our I minus 1 over our Z, but we're going to have 4 pi times the K of ice right here. Okay, so worst case, if it was saying it's all ice, right? Now,
So in that case, it would actually increase the heat gain.
yeah, because the K of ice, we can look in the back of our book in the tables for what the thermal conductivity of ice is, and it's about 2 times thermal conductivity of insulation, of this insulation. So that would basically double our heat gain. Okay, it would shrink our resistance, by 2, and basically double our heat gain.
So at that point, it's essentially like putting your liquefied petroleum in direct contact with ice, right?
Yeah. Yep. So we're doubling our heat gain. So we don't want that, right? Because you want to basically keep this liquefied petroleum gas as a liquid, right? Because this is typically done to store it or to transport it, because in liquid form it takes up way less space than in gaseous form. So liquefying it allows it to be, much smaller storage tanks. Okay, so we want to keep it in liquid form. So with this higher heat gain, we'll try to transfer it more to vapor. We either got to put in energy to bring that vapor back to a liquid, or help with this, reducing this heat gain. Okay. So how could this situation be avoided, right? So that's where we don't want this water to make its way, to keep making its way there to build up that ice, and that's basically with a vapor barrier. And then it's just a surface that doesn't allow water to transfer it through. So put that on the outside of your insulation. Any questions? All right, so we did an example with Cartesian coordinates. We did an example with cylindrical coordinates, and we did an example with spherical coordinates, but we also really solved different things and did different setups within the thermal circuits between those, but it's all thermal circuit setup to solve these problems, okay? But we just solve for different parameters